This is The Element, a visual exploration of every known atom in the known universe. I say known universe because this is all we can see. Today we're starting off our exploration with number 91, PROTACTINIUM. Now, PROTACTINIUM is the last of the naturally occurring elements that are, well, seriously annoying element collectors themselves, according to the author. Unlike the other ones, like acetine, francium, and actinium, PROTACTINIUM's half-life is long enough, like 32,788 years. That's how long it takes to, decay into half of its mass. And it's it's lump large enough to see, which is really useful. Also, it is dangerous. It would be really practical to show off in a nice lead-lined display case, but that's the thing. It's a lead-lined display case. It is. Yeah, that's the frustrating thing. You cannot display it at all. This makes it unavailable. It makes it unavailable, which makes it even more frustrating itself. About 125 grams of it was put together in the 1960s, and it was distributed towards laboratories around the country and the United States of America who just wanted to study it for some reason, and they wanted to put it into practical applications, unfortunately. So, because to this day there are none, yeah, there's this guy still waiting for some leftover protactinium on eBay. Protactinium in the form of the very short-lived isotope like protactinium-234, which is the half-life of 1.17 minutes. This was discovered by Casimir Franz and O.H. Gonichong in 1913. This was the much long-lived isotope of plutonium-234, and this was independently discovered in the 1918 by Frederick Soddy and John Cranston in Scotland, and Otto Hahn and Lisa Meitner in Germany. They all independently discovered it, and so of course, they would really want to name it them by themselves, make it theirs. Soddy discovered that it's possible for all these different atoms of the same elements to have different masses, and lived to kind of regret it. An element is defined as a substance. It's like a substance of a pure form, created only by one atom, which nuclei contains a specific number of protons to determine what it is. But all nuclei, except H1, also contain a neutron, with the exception of hydrogen, as I mentioned earlier. Each isotope of an element has the same number of protons, but it has different numbers of neutrons, and yeah, that's it. That's the only difference, different numbers of neutrons. And ions have different numbers of electrons. The number of neutrons in an atom's nucleus, it doesn't really matter towards their chemical properties, but it does matter to their nuclear stability. If it has a little bit more neutrons than normal, or a little bit less, or just the right amount, it will go ahead and not decay. But if it has too much or too little, boom, there's a nuclear stability. Depends how long, so it depends on how many neutrons there is to determine how long that neutron instability is. And when atoms disintegrate, which is called fission, a huge amount of energy is released, and energy that is the basis of both nuclear power plants and the nuclear bombs. Yeah, unfortunately, there was this guy who figured out how much energy that would create, and eventually, well, they created the bomb. Its atomic weight is 231.03588, its density is 15.370, its atomic radius is 180 picometers, and its crystal structure, it's a centered cuboid, not even cube. 7s was filled up, so now we're moving on 60. Please fill it up. And it has a high, alright, for actinides, it's high melting point and a really high boiling point. Next up, I have uranium, number 92. Uranium, it's the radioactive element most commonly associated with Big Boy. The nuclear bomb, Fat Boy. I think was it Fat Man or Fat Boy? Whatever. It was basically nuclear bombs. It's impossible to discussing uranium without first acknowledging atomic bombs. Atomic bombs themselves have created a name for themselves because of their destructive nature. Yeah. All of these, the first one was the uranium fission bomb, built in secret deep in the deserts of New Mexico and detonated over the unsuspecting city of Hiroshima on the Honshu Island of Japan. I don't think they ever recovered from that. The Great Wall of China and the Apollo moonshots were large undertakings, but this was an even larger one too. It would measure an irreversible consequence that would shake the whole planet. And there was this one thing, and a part of it ignited the atmosphere. It would create nuclear fission on the larger scale, destabilizing the entire atmosphere, leaving the Earth atmospherous, meaning there is really no air for humans to breathe, and within 8 minutes, solar radiation would hit the Earth, and boom, it's gone. Why did we create all that? Because we're idiots. And who built this? The scientists at the Manhattan Project. And for some reason, people somehow printed photos with uranium salted photo paper, and the print itself is really radioactive. Tiles behind drinking fountains at the Art Deco school that this offer went to had small amounts of uranium in it for some reason. You might know uranium as the greenish material, but sometimes pure uranium metal is perfectly legal to own, up to 50 pounds at one time. And there are actually a few companies that sell it to element collectors. This 30-gram piece came from one such company. Be careful though. It has an atomic weight of 238.02891. Its density is 19.050. Its atomic radius is 175 picometers. And its crystal structure, it's a cuboid. Yeah, I don't really see much difference other than 5F. It went up. I really hope it gets full. If it's not full, well, boom. This is a nuclear reactor fuel pellet that contains uranium enriched in uranium-235, and this is not legal to possess without a license. Number 93, we have Neptunium. Neptunium, named after the planet Neptune. Uranium, named after the planet Uranus. You may have noticed a trend over the last 9 elements. They are all radioactive, but the odd-numbered ones have very short half-lives, while the even-numbered ones last very long. In some cases, billions of years. Yeah, this trend continues all the way to berkelium, and is due to the fact that protons and neutrons pack themselves in certain ways. Thus, noble gases are chemically stable because they have just the right number of electrons to form a complete outer shell. The nuclei of even-numbered elements in this range have the right number of protons and neutrons to have a stable configuration, at least stable enough to last for thousands or even billions of years. Another trend, though, although it is short, is that Neptunium, plutonium, and uranium, they're all named after planets. Uranium was discovered in 1789, and that's why it was, named after Uranus, because, it was discovered 8 years before that. The fact that we've discovered uranium before, in 1789 is kind of disturbing, because radioactivity wasn't discovered until, 1895, which is, over 100 years later. Yeah, that is quite alarming. And then Neptunium later was discovered too. Neptunium was the first transuranic element, the elements after uranium, that was discovered. It was discovered in 1940 at the University of California, Berkeley. And by convention, uranium is the last naturally occurring element in the entire world. But in fact, very tiny amounts of neptunium should exist in uranium-bearing minerals due to nuclear side reactions triggered by, uranium's decay. There are no common applications for neptunium, though. In fact, most of the elements you'll see from now on are only used for laboratory uses, and even then, it's really hard to make. I think we only made organism once, and we've never made it again. There is one thing, though. You certainly have some in your smoke detectors. Smoke detectors use a small amount of americium to generate alpha particles, and that's all there is to it. So, neptunium itself, you'll find a lot of it accumulated inside it, because americium will decay into neptunium. Its atomic weight is 237, its density is 20.450, its atomic radius is 175 picometers, and its crystal structure, it's a cuboid. And 5F is going up. Very unsatisfying to my eyes. Surprisingly though, we were able to measure its melting point. For some reason, we melted it. And next, we have plutonium. If you read that, caution. Plutonium 288, less than 3 Curies 1878. Do not discard. Contact near Nuclear Battery Corp, Columbia, Maryland. Date of manufacture 1973. Serial number AA237-8. Obviously, this is plutonium, and plutonium itself, it's incredibly fortunate that it's saying that we make atomic bombs. Making atomic bombs is so difficult, mainly because if it was so easy, we have a bunch of them right now. A uranium-92 atomic bomb is hard to make, mainly because of uranium-235 isotope you need is extremely expensive to separate from the much larger amount of useless uranium-238 you find in nature. And that is still expensive. Expensive as in, if you're not the government of an advanced nation, you really cannot afford it. Which means that only a handful of countries have uranium bombs, such as United States of America, Russia, just to name a few. But if you can get yourself to the critical mass of uranium-235, it's pretty easy to make the gun. All you need is to build a cannon that shoots one lump of uranium into another, and boom, you got the atomic bomb. But where are you going to get that uranium-235 is my question. Now, making a plutonium bomb might seem much easier because it's not so hard to get this plutonium bomb. And of course, sure, you need a nuclear reactor, but it's child's play when compared to isotope separation, of course. In fact, at least one child has seriously tried himself. David Hahn constructed a breeder reactor for his Eagle Scout project in 1995. And this got into a really big trouble when people realized it wasn't just a model. Some people think that his miniature reactor might have actually worked. So apparently, a teenager can do it. Why not? Why not any random adult who has some knowledge of physics and chemistry? Although it is really easy to get plutonium, by some unfortunate coincidence, so it is really hard to turn it into a bomb. Unlike uranium, though, you can't just like shoot it at each other. By the time the friction goes ahead and melts the two things, it will just have, well, it won't work. It will probably spread radiation all over the city where you intended to bomb it, but other than that, it won't melt it. What you have to do is that you have to implode each other into it to make an explosive lenses, which have to be nearly perfect. If they're not, well, boom, you got radiation, but you don't have the fire. Any asymmetry in the shockwave gives the plutonium a little way to sneak out the outside. Even today, a plutonium fission bomb requires state-of-the-art metallurgy with prior techniques and fabrication technologies. Any amateur plutonium bomb would almost certainly fizzle, unless you're that kid who tried to create the plutonium bomb. Plutonium generator, nuclear reactor at least. And then the people at Los Alamos actually published a paper against plutonium's reputation for being the poisonous element because for some reason they were pretty hurt by it. What is undisputed is that private ownership of plutonium is absolutely forbidden, except one tiny exception. Pacemakers today use lithium batteries, but a few people, no one knows exactly how many, still have models powered by the plutonium thermoelectric batteries. If you have one, you're allowed to keep it until you die. And, well, according to the author, I'm quoting his book, and I swear this is true. I got emails from undertakers asking me what to do with the radioactive pacemaker they found in one of their clients. As tempted as, well, he might be to just go ahead and invite them to send it to his collection, he still told each one that by law, all plutonium must go home to Los Alamos, where it will be loved and cared for. Lo. It has an atomic weight of 244, its density is 19.816, and its atomic radius is 175 picometers. Its crystal structure is an oblong cuboid, and, well, 6D has gone down, but 5F has gone up, and we have, for some reason, measured its melting and boiling rate. I'm not even going to mention atomic emission spectrums now. They're just not worth it, in my opinion. Next up, we have Americium, number 95. America, the land of captains. Avengers, Iron Man. Actual Iron Man. Also, France technically made that first. You might think that a synthetic radioactive element that follows plutonium and has a significantly shorter half-life would be some kind of super bomb too, available only towards scientists in secret laboratories. And maybe someone's trying to go ahead and study Americium in a secret lair somewhere. However, you could just simply go into your neighborhood Walmart store and buy some. As I mentioned earlier inside the plutonium chapter, or was it Neptunium? Neptunium chapter, we went ahead and explained to you that Americium is inside a bunch, lots and lots of fire detectors, smoke detectors. That is kind of very, very surprising, you might think, when this is so radioactive. Thing is, it just melts into plutonium after a while, but it's safely put inside the smoke detectors too. The reason is that not that americium is fundamentally less dangerous than the elements around it. In fact, it is the most commonly available isotope, is more radioactive than weapons-grade plutonium, and at least it's toxic. The difference is that there is a useful application towards americium that requires only a very tiny amount, and for which a company was prepared to go through to get and carve out a really big exception. Ionization type smoke detectors contain a tiny foil button, quite similar to what we find in the anti-static brushes. However, instead of anti-static brushes, we kind of get this. We get a sensitive americium inside there. The americium should, for some reason, help with all this. But should we be worrying about radiation leaking into our homes? I don't think you should. As long as it's inside, you should not worry. Its atomic weight is 243, we don't know its density, for some reason, and there's an atomic radius of 175 picometers. Its crystal structure, it's a hexagonal prism. And, atomic emission spectrum doesn't really last that long. 5F! Oh, come on, 5F! Come up, go up, go up, go up! And it has roughly 1,100 degrees of melting stuff. I'm pretty sure this is in Celsius. And its boiling point is about 2,000. And that is it. I hope you guys enjoyed this episode. I hope to see you guys soon. And so until next time, Shanano, peace. Bye bye.